we're going to move over to the milling side and talk about high-speed machining, and it's going to cover solid carbide end mills for the most part, and how we've partnered to make some high-speed machining approaches a little more easy to program. And I think you'll see between the dynamic milling and between utilizing some unique hybrid style solid carbide end mills, we're enhancing the high-speed machining process. So I just want to start out by, I want you to think about, if you're looking at these pictures here, we've got a tool that's engaged a little bit more than 50%. And then you've got one down here that maybe is engaged 5%. And we've got a 4130 material, and we're taking a 4-flute end mill, 3 times D type gauge length, and we're moving along. I want you to think about the difference in programming. Like, what would you program feed speed, depth of cut, width of cut in this situation compared to this one? Bring that up because we could go around this room and you would come up with a different answer for pretty much everybody. I'm going to pay attention to the motion of this tool path, different speed and feed changes after the entry move. The feed rate on that was 850 inches programmed. And program feed rate and actual feed rate are two different things, and something that's easy to do when you're programming in Mastercam. If you ever want to know how efficient you are when you're applying a tool path like this, just go down to the info button on the back plot and look at the amount of feed that you've traveled, and then divide that by your cycle time, and you've got what you've maintained for in inches per minute. I could tell you that in this, we programmed at 850 inches per minute. After we did the math with the slowdown of the machine, we were still maintaining 750 inches per minute. So it was pretty good. But how do you run tools like this? It's something that, like, once again, you could go around and ask everybody in the beginning, if you were going to run that part 5% step over with a 3/8 end mill, what would you end up running at? By the way, that's a 3/8 end mill in that video. And what depth of cut would you take? Well, we want to say we're changing the approach to take advantage of what the software companies like Mastercam are bringing to the table, like dynamic milling. And so with high efficiency machining, where do we start? What are the keys to it? One is end mill selection. We want to use as much of the flute as possible, so we want to base on depth of cut. And we want to use up to 100% of the flute. With the old Z-level machining tool pass, you might use half the flute or a quarter of the flute, and as you're working your way down, you burn up the end of the end mill. So rather than do that, we want to use 100% and change the game. Go to a small width of cut and a large depth of cut. We want to choose rigid tool holders. I'll show you a little bit about that as we go on. Well, we want to choose a baseline speed and feed. The reason I'm saying baseline, I told you to think about what you'd program an end mill if you were cutting a full slot. When we get into the Hcm factors and the dynamic mill enhancements, the math has to start from somewhere. So when you start out down this road of high efficiency machining inside Mastercam, your starting point will be the baseline speed that you would program an end mill out of the catalog. You can look in the ISCAR catalog, say we're cutting that material, and this is the speed they recommend for a full slot application. Choosing your baseline feed, same thing I just said. Get it out of the catalog as to what it would be for a full slot application. And then we want to look at what's going on with your company. The best case scenario is not the same for every company. You all have different machine tools. You got to find out what that machine tool can handle, and you'll see as we go up in what we call these Hcm factors that the speeds and feeds they grow exponentially very quickly. So you have to maintain, and there's things inside of Mastercam that help you maintain what the machine tool is capable of. And do not proceed without the proper programming. If you try to do this and you start jamming the cutting tool in the corners and whatnot, you won't have a cutting tool. So I'm going to go through the Anvil selection. Using 100% of the tool, we want to use as much of the fluid as possible. With the holder, what you're seeing here is a very rigid holder. This is a short end holder. You'll see that we've taken away the projection, and we have the collet up inside the holder. This is the most rigid gauge line type situation we can come up with. You know, something that if you're roughing like what you saw in the video, a lot of times we get hung up on shrink, shrink, shrink. Well, shrink usually has a projection. I can tell you that if you want to increase tool life and the machine tool allows it, I know there's some machine tools out there that you can't apply anything but a shrink holder. I would recommend collet holders, and I would recommend mill chucks. And the reason is more mass. You're gonna have less deflection, and you're gonna have better tool life. By the way, if you're getting this aggressive with a collet holder, make sure you wipe the tool off and the collet off with some alcohol before you get going, and give it a good wrench, because you can pull end mills out of these. Checking and matching the results of machine capabilities. We just want to make sure that you know, we understand that some high-speed machines, you don't get to their threshold until you get the RPMs up to a certain number. And then again, the dynamic machining, dynamic milling. This is an arcing tool motion. You're going in and out of the cut. Something to keep in mind, and I'm sure Steve will show it to you, as this tool arcs in and out of the cut, you'll see that the motion and the feeds and the speeds change dramatically, and that is to optimize air cutting time. We don't want to cut air at the same speed and feed we're cutting steel. Just a few more pieces, and I'll turn over to Steve. You know, carbide comes in different grades, different shapes, different forms. We apply chatter free, which is variable pitch, variable helix type technology, and also this all-in-one end mill. If you're doing pocketing, if you look at this all-in-one end mill, we've got a high feed geometry on the tip, which is hard to see here. We've got variable pitch, variable helix on the flutes, and we've got chip splitters to help with chip evacuation. I think that, you know, you're looking at a two-in-one end mill. You're looking at an end mill that can do 2D and 3D applications. But the thing for me is, from a programming standpoint, if I'm doing a pocketing application, if I'm ramping with a bullnose end mill, I'm wearing out the tip of the tool. If I do it with this tool and I maintain the feed geometry on the tip of the tool, I've got two separate cutting zones. I've got a high feed cutting zone, and I've got the side or the flutes of the end mill for the 2D shape. Right now, with the Hcm approach, we're saying this covers P and M material categories. You know, we've done some things in high temp, some titaniums, things like this, but it's a work in progress. The high temp formulas for increasing the speeds and feeds will be part of future releases. So, is what I just described real easy to apply? You know, you're talking about, we've got experimentally determined information that we're supplying you. We've got feed optimization. We've got speed optimization. And we've got a lot of calculations. And with Mastercam, we want to take the calculator out of your hand, keep you programming, and increase your efficiency from a programming standpoint. I just want to, real quick, little case study. We've got a partnership here, and one of the Mastercam resellers and a NISCAR guy went into one of our end users, and the real benefit is, are we creating a cost benefit? Are we saving money? Are we getting parts out the door faster? What are we doing? Here's a aerospace type part, and it was 13/8 material. Came into the customer, they were working at 22 hours per part in and out the door. After we got done, we were down around 10 hours. Total cost per batch went from just under $1,800 to a little over $1,000, and they were very happy. I'm going to turn it over to Steve, and he's going to show you the guts inside of Mastercam that take care of this programming.
So I have a part here that I've already programmed using our dynamic motion. Let's just first start talking about the dynamic motion itself. Now let's take a look at the tool's motion. As we enter the part, and I don't know if you can see this, in fact I'll probably turn the shade off so you can see it a little bit better. We start coming into a situation here where you can see you can start seeing the motion. It's not circular. It's more, I guess the better way to describe it is it's more of a D motion. And as you can see, I'm walking my way through, and as I come out of the cut, the tool is actually going to lift up, so I'm not scrubbing the floor. So that's the basis of the dynamic motion. You notice that we isolate the regions. One thing that we say that dynamic motion does over any other toolpath is we know where the stock is at any given moment. And I think that's a critical differentiator. So let's get into the guts. Let's talk about how we get there. Let's look at some of the interface first. We call these toolpaths dynamic. And dynamic means it changes based on the topology of the part and on the stock. If you're a Mastercam user, you recognize these dialog boxes. And what I've done here is I have an ISCAR tool loaded. And you'll notice that this becomes available. If I were to change the tool, for example, go to just a regular 3/4 inch flat end mill, you notice these buttons and switches here, these toggles go away. They're only available when I select the ISCAR series tools that are applicable for the Hcm motion. And you'll notice that I have a toggle right here where I can turn on or off. And you'll also see a slide bar here. And you take a look at it, you see as I move this slide bar, there you see there's this thing called the Hcm factor. This is the empirical data that ISCAR has developed through their testing. And as I slide this slide bar over, not only does the Hcm factor change, but the feed rate changes as well as the spindle RPM to maintain that constant chip load. So what you'll need to do is still import the feed per tooth and SFM information that you can get that from the ISCAR catalog. And then you'll enable the Hcm. And again, this is a fail-safe approach to using this tool appropriately. Let's go through some more of the parameters here. And let's talk about the specific motion itself. You can see we have an approach distance. And you'll also notice when the Hcm is applied, I only have 3 options for my toolpath step over amount: 10%, 7%, and 5%. If I change this to 5%, and perhaps go back to my tool, and I'm going to bring my Hcm factor down to 1, you'll notice that my feed rate is just about 147 inches a minute. If I go back to the cut parameters, change that to 10, it makes sense. We're just at 71. Let's go back to some of the motion. We also have what I mentioned earlier, the micro lift distance. And what is that? Well, essentially it's this motion, this straight line motion, as we are not in the material, we're free of material. I will not only lift the part or the tool off the part so I'm not scrubbing the floor, but I'm also going to increase the feed rate. So I lift it, in this case, 0.010 of an inch. And then I have my back feed rate, or my free feed rate, at 500 inches a minute. Entry motion, how we enter the part is important. We have many different options here. As you can see, we have a helix entry. Another entry that perhaps works quite well is a profile entry, where we're actually creating a trough or a slot where we're coming in and we're ramping in. Or we can create a custom entry along a piece of geometry that you've defined. Again, if you're a Mastercam user, you recognize and already know how to use all these parameters. I just want to add one more thing. In part of our testing, when we went out to our customers, we wanted to make sure we had some metrics to try to prove out some of this capability so that it's easier to justify. We went to one of our customers that was creating mold plates using regular off-the-shelf mold plates. He was using another type of cutter. It was taking about 1 hour and 5 minutes. We changed to an ISCAR feed mill, not using the Hcm application. It was multiple pockets. We brought it down to 45 minutes. That's a pretty good savings right there. Then we applied the Hcm calculations. Same tool, same part, same machine, 15 minutes.